Now we're going to look at these two integrals. Let me apologize. I know that the sound quality is bad, but I cannot log into Zoom on my regular computer. This is a problem that should be fixed in the next few days, but there's going to be 2 days of lectures at least that are probably going to be plagued by this bad audio. So we just want to do this iterated integral. And one of the things that I want to point out is that there's a trick that we can do to kind of make things go a little faster. So we're going to look at, again, we're going to do what we did last time. This is the integral from r is equal to 2 to r is equal to 3. We're going to sort of ignore the outer integral for a moment, and this is the integral from phi is equal to 1 to 2, r phi d phi, and then dr on the outside. Now notice that as far as phi is concerned, r is a constant. So just like we do with other constants, you know, like the constant 17 or 3, we can move this on the outside of the integral. And now I can abstract even more and really just concentrate on what I need to in the inner integral. So let me put the brackets, dr. So now I'm doing the integral of phi from phi is equal to 1 to phi is equal to 2. Now the antiderivative of phi is phi squared over 2. So this is going to be, and we're going to, from phi is equal to 1 to phi is equal to 2. So this is going to be 2 minus 1, or 2 squared minus 1 over 2. That's 4 minus 1 over 2. That's 3 halves. So now I have an r integral. 3 halves is a constant. So this is going to be 3 halves times the integral from r is equal to 2 to r is equal to 3, r dr. This is going to be equal to 3 halves times this integral. The antiderivative of r is r squared over 2. So let me go ahead and write the 1/2, and we're going from r is equal to 2 to r is equal to 3. So this is 9 minus 4. So what this is 15 over 4. Now I'm going to do this integral. Now notice, just like the last example, this is very similar, but the order of integration is different. So this is the integral, phi is equal to 1 to 2, and in the integral, inner integral, this is the integral r equals 2 to 3, r phi dr d phi. And again, as far as r is concerned, phi is a constant. So I can pull this out. So now this is the integral, phi equals 1 to 2. The antiderivative of r is r squared over 2, and we're going from r is equal to 2 to r is equal to 3. So this is 9 minus 4 over 2. That's 5 halves. And then I need to remember to write the phi. So this is 5 halves times the integral from phi is equal to 1 to phi is equal to 2, phi d phi. The antiderivative of phi is phi squared over 2. And we're going from phi is equal to 1 to phi is equal to 2. So that's 4 minus 1, which is 3. And again, this is 15 over 4. Okay, and this brings us to Fubini's theorem. So notice that in the previous two examples, oops. Well, I did not mean to do that. Sorry, I deleted what I just wrote. You can just back up the video a little bit if you want to. I do not want to do it again. Okay, so now what does Fubini's theorem says? What does Fubini's theorem say? It says the following. If f of xy is continuous, then the following fact is true. The integral from y equals a to y is equal to b times of the and then so this is an iterated integral. The integral x is equal to c to x is equal to d. F of xy dx dy. This is equal to the other iterated integral, meaning the integral from x is equal to c to d. The integral y equals a to b f of x comma y dy dx. And there are actually more general versions of Frobenius theorem that we will get to when we look at more general versions of integrals.